So I will present the paper Registered Transducers are Marble Transducers. I'm Gaëtan Douéneau-Tabot. I'm a PhD student under the supervision of Olivier Carton at IRIF, and I wrote this paper with Paul Gastin and Emmanuel Filio. In this paper, we studied transducers, and I will first give generic motivations for the study of transducers. Finite automata have been really important in theoretical computer science because they allow to model simple programs, programs that have a finite memory, and that either accept or reject. So basically, it's functions from the free monoid to true or false. And with this automata, you describe regular languages, and all the questions you can ask turn to be decidable, so equivalence, membership, and all these decidable results are very useful if you want to do program verification when you model the program by an automaton. In order to go beyond, we consider transducers, which are finite automata enhanced with an output mechanism. So basically, during its computation, a deterministic finite automaton will also produce a sequence of letters that will form a word, and this word will be defined as the output of the transducer. So a deterministic transducer will model a simple program that produces an output. It takes as input a finite word and produces a finite word as the output. And this is more interesting than only modeling programs that accept or reject. But however, the situation becomes more complex when it turns to decidability and good properties. And it's what Dana Scott noticed more than 50 years ago. So I let you read the quote. It basically says that machines that produce an output are more interesting to study than machines that just accept or reject. As we want to model simple programs using these transducers, we can define some conditions, some properties we would like to have for our transducers. So first, we want our transducers to be easily implementable in practice so that they can be useful. Then for program verification, we may want to have a decidable equivalence problem. That is, if we take two transducers, two programs, we may be able to decide whether they compute the same function or not. Another property we may want is a decidable membership problem. So membership problem is basically the question, given a function computed by a machine in a big class, can this function be computed by a machine in a smaller class? So in terms of programs, it can be interpreted as can a function computed by a complex program be computed by a simpler program? And basically this question in practice is that of program optimization. And if we are able to have membership results for our transducers, then we will be able to perform some program optimization or program simplification. More specifically, in this paper, we intend to study marble transducers, which is a model that was introduced by Engelfried in 1999. And we shall see that this model has all the good properties we listed above. That is, it has an easy implementation using the model of streaming string transducers that we show to be equivalent, and this is a well-known model of transducers as well, but the equivalence was not known. It has a decidable equivalence problem because of streaming string transducers that have a decidable equivalence problem, and we also show that it has several decidable membership problems that can be reformulated in terms of program optimization. For the outline, I will give in the first section some context about regular function, and then the contributions will be detailed in the second and third sections. In order to understand our model of marble transducer, we first need to understand what is a deterministic two-way transducer. And if we look at the drawing, a two-way transducer is just a finite control memory plus an input tape and an output tape. On the input tape, there is a two-way reading head that can move left or right. And this head is read-only, that is, it cannot write anything on the input tape. So this part with the control memory and the input tape is a two-way automaton. And we add an output mechanism to this automaton, that is, it can write outputs, but these outputs are done in a one-way fashion, that is, once a letter is output, it's definitely written and it cannot be written or read again. This two-way transducer computes a function from finite words to finite words. If you put a finite word on the input, then you will produce on the output a finite word. And we only consider computations that terminate. We don't want to have infinite behaviors, so we have a function from words to words. Now let me give an example of a two-way transducer to compute a function. So it's the mirror image. Basically, you take a word and you produce the same word but read in the reverse direction. How do we do this? We shall do it with a right to left reading. The moves of the reading head are depicted in blue. So it starts at the leftmost letter, it will go to the rightmost letter, and then read the word from right to left, while outputting the letters it sees. So it exactly, by definition, produces the mirror image of the word. Okay, now regular functions are the functions that can be computed by deterministic two-way transducers. They have been intensively studied in the literature, and it has been shown that they have several good properties and good decidability results. Let us note just that they have a linearity property. That is, if I give an input of size n to a two-way transducer, it has at most big O of n configuration on this input, and if we avoid looping behaviors, it will thus produce an output of size at most big O of n. So the functions computed by these transducers, the regular functions, they are at most linear in terms of size of the output with respect to the input. However, two-way transducers are not really useful in practice, exactly because they are two-way. In fact, they can go to the last letter of the words and come back to the first one. And this is not a streaming model. By streaming model, I mean something that processes the input only once in a left to right fashion. And streaming models are especially important in practice, and it's a natural question to ask whether such a model exists for regular functions. So let us see how we could implement the mirror image in a streaming fashion. Well, a simple idea is to use an accumulator, a register X, that will store the mirror image of the prefix we have currently read. That is, first, before reading the word, the accumulator is initialized to epsilon, the empty word, and then after meeting an A, we set X to A. Then after reading a B, we set X to BA. Then after reading another A, we add it in front of X, and now X is ABA. And so on. After that, X is AABA. And finally, we can output the value of X, that is, the mirror image of the input word. And basically, this idea of using registers is exactly that of streaming string transducers. So we now define more formally this model of SST, or streaming string transducer. It's a one-way automaton plus register. So now the finite control memory has a reading head that can only move on the right. So it's a streaming machine. And it also has a finite set of registers. So here it's X and Y. And these registers store finite words from the output alphabet. And each time a new letter is read, the registers are updated using substitutions. So for instance here, X will take the value BXYA, that is B concatenated to the former value of X, the former value of Y, and then an A. So basically it's the way we update the registers. And at the end of the run, at the end of the word, the registers have some finite values, and the output is defined as a combination of these finite values. And if we consider again the mirror image and its implementation by a streaming string transducer, we need to use these two substitutions. That is, if we read an A, we add an A before X, and if we read a B, we add a B before X. However, streaming string transducers can describe functions that are not regular. Why? Because these functions have a growth that is more than linear in the sense of the size of the output with respect to the inputs. The most easy example is that of the exponential. You take a number written in unary and you want to output the exponential of this number, so a to the n, and you want to output a to the 2 to the n. And to implement it with a streaming string transducer, you can use the substitution x takes the value xx, and if you start with x initialized to a, each time you win a new a, you will be able to multiply by 2 the value of x, and so you will produce the exponential. But the thing we do here is that we copy twice the value of x. And the idea in order to obtain linearity and only regular functions is to forbid these copies. That's why Allure defines copyless SSTs as streaming string transducer that can only use copyless substitution. And basically, a substitution is copyless if each register appears only once in the right number. That is, when we perform the update, we have only one place where we can use the value of a register and not twice. And obviously it's not the case of the substitution x takes the value xx, because x is used twice. We can now state the main result of Allure, that is that copyless streaming string transducers compute exactly the same functions as deterministic two-way transducers, that is, regular functions. And so we have a streaming implementation for these two-way transducers. However, this result is not simple because it requires some work on the machines. So to summarize this section, we have copyless streaming string transducers that correspond to two-way transducers. And above this, we have a larger class of functions, which is the class of functions computed by streaming string transducers. And our objective is to detail this class and understand it more precisely using marble transducers. Present our contributions about first marbles and streaming string transducers. The first question we shall address is, can we extend the correspondence between two-way and copyless SSTs by finding a two-way model for SSTs in general? To answer this question, we introduced the model of marble transducer that was defined by Engelfried, and this is a two-way transducer plus a stack of marks that are named marbles that can be dropped on its input. So on the picture you can see just a two-way transducer with its control memory, its output tape, its input reading heads that can move right or left, and it also has the possibility to drop marbles on its input. So here you have two colors of marbles that are blue and purple, and you see that in the current configuration there are 3 marbles dropped on the input tape. When in a given position of this tape, the machine has the possibility either to move right or to move left, or to drop a marble of one of the colors, or to lift a marble, to remove a marble that would be present in the current position. However, it's not possible to move right if there is a marble in the current position. This is shown by the red arrow that is above the input tape. If you don't remove the marble, you are forced to stay on the left of this marble. In a nutshell, you can store a stack of information on your input, but only at the right of your current position. Let me now give an example of what we can do with marble transducers and consider the function multiple concatenations that takes as input a word W, a separating symbol, and a certain number k of A's, and that outputs k copies of W hash. To implement it with a marble transducer, the idea is to drop successively the marble on each A. So first, we move to the first A, and we drop the marble in this position. Then we go back to the first symbol, and we read again W hash, and we output it. Then we meet again the marble. We lift it, and we move to the next A, and we drop the marble in this position. We do again the same procedure, that is going back to the first letter, outputting W hash, and going to the marble. And we go on like this, moving the marble on each A. Note that we always stay on the left of the marble. Also note that this function multiple concatenations is not linear, but in fact quadratic, hence we can do more than regular functions with these marble transducers. Let us now see how to do the exponential. The idea is to count in binary on the input by going from 0 to 2 to the n minus 1, using two marbles, 0 and 1. First, we drop the marble 0, 0, and 0, what makes the number 0 on the input, hence we can output an A. Then we increment this number to 1 by changing the first marble from 0 to 1, and we can output another A. Then we want to write 2, hence we remove the first one, and we change the first 0 we meet in a 1, and finally we complete with zeros and output an A. The next step is to write number 3 by changing the first 0 in a 1. Then number 4, and so on and so on. Note that all these steps can be performed while preserving the stack discipline of the marbles and without going on the right of a marble. The two former examples give an intuition of the main result of our paper, that is, streaming string transducers with copies are equivalent to marble transducers. Furthermore, the conversions are effective. The proof of this result is inspired by the proof of the equivalence between copyless streaming string transducers and two-way transducers. Before going further, we can summarize our results this way, and we are now going to fill in the big white circle with a sort of hierarchy. Indeed, note that the exponential has an exponential growth, whereas the mul function only has a quadratic growth. Hence, there may be a difference in the way they are treated with marbles and streaming string transducers. We are now going to describe a hierarchy of classes of functions depending on their growth. A natural restriction of marble transducers is the notion that we introduce as k-marble transducer. A k-marble transducer is a marble transducer that never has more than k marbles simultaneously dropped on its input. For instance, a zero marble transducer is a marble transducer that never has a marble on its input, hence it's just a two-way transducer. Concerning one marble transducers, note that the function multiple concatenations that we saw before was computable by a one marble machine because we only had one purple marble that was moving from one A to another and we had no other marble. And intuitively, a one marble transducer corresponds to two nested loops, two-way loops, of the form for y in 1 to n and for j in 1 to I. Indeed, I represents the marbles that can move from 1 to n, and j can be seen as the reading head that is forced to stay from 1 to I, the position of the marble. We saw that multiple concatenations can be computed by a one marble transducer. And we are now going to see that it can be computed by a really simple streaming string transducers that make copies, but not too much. Indeed, it will have one layer of copy, so we will define this. And the idea is the following. So the transducer will read the whole input, and after reading the hash symbol, it contains W hash in the register X, and the register Y contains the value epsilon. And then each time we read an A, we add a new X in Y. So Y is updated by taking the value YX. And finally, Y contains W hash K times. We say that this streaming string transducer has one layer of copy, or is one layered, because its registers can be partitioned in two layers, X in layer 0 and Y in layer 1, and in layer 0, X is never copied twice in itself. In layer 1, Y is never copied twice in itself, but possibly there are copies from layer 0 to layer 1, that is, X can be copied in Y. What is important is that this definition of layered SST restricts the way we can do copies in the registers. Our second main result is the following. For all k, we can define a notion of k-layered SST, that is, SSTs with some restrictions on their copies, that exactly captures the power of k-marble transducers. And all conversions are effective. This result is far more difficult to show than the first one because it uses more precise techniques than just the conversion between marbles and streaming string transducers. When k equals 0, we exactly recover the equivalence between two-way transducers and copyless streaming string transducers because in fact zero-layered SSTs are just copyless SSTs. In a nutshell, we have shown that there is a polynomial hierarchy of streaming string transducers between copyless and full streaming string transducers that corresponds to 1 marble, 2 marbles, 3 marbles, etc., etc. We noted that regular functions had only a linear growth because two-way transducers could only have a linear number of configurations on some input of size n. And in fact, the situation is quite similar for k-marble transducer. It's not hard to see that a k-marble transducer is somehow k plus 1 nested loops, and for this reason it can only have big O of n to the k plus 1 possible configuration on some input of size n. Therefore the output is at most of size big O of n to the k plus 1. For instance, we noted that multiple concatenations had a growth big O of n square, and indeed it was computable by a one marble transducer. A natural and interesting question is to know whether this growth, this size of the output, is a sufficient condition for being computable by k marbles. I mean, if my function has size big O of n to the k plus 1, does it automatically mean that I can compute it with only k marbles? Finally, we have this big picture where each layer of the hierarchy in fact corresponds to the growth of the output in terms of polynomial. To conclude in a nutshell, we first note that our result implies that equivalence of marble transducers is decidable, what was not previously known. Indeed, the equivalence of streaming string transducer is decidable and both models are equivalent. We obtained elegant and fruitful results for marble transducers, and these results are worth being extended to other classes of functions. For instance, we could study pebble transducers, which are a variant of marble transducers, and the membership problems are solved with somehow similar results to ours, even if the proofs are very different, by lot in leaks this year. However, the equivalence problem is still an open problem for these pebble transducers. We could also study several extensions of our models, using, for instance, data words or having more operations on the registers. And it could also be fruitful to implement practical versions of our procedure because they can be interpreted in terms of program optimization. Thank you for listening to this video and feel free to contact us by email if you have questions, suggestions or comments.